In this lecture, we're going to talk a little bit about graphing. So let's take a look at this as our first sample graph. So this graph has some problems. So let's discuss a few of the problems with this graph. So for one thing, you may notice it doesn't have a title. We always want to have a title on our graph that describes what this graph is showing. A second problem with this graph is that we don't have any kind of labels on our two axes, our x and our y. A reminder, in case you're not good with graphing, x is your horizontal axis and y is your vertical axis. So this one has no labels, so we have no idea what this data is even representing. Now it is okay that the scale on our x is different than the scale on our y. However, we actually can't have 0 in two places. So if this is 0 for our x, we can't also have a 0 up here for our y. 0, 0 should be an intersect point. And finally, you may notice this data kind of goes up and down. Now for our class, we're not going to do a lot with this, but in real science experiments, typically with data like this, we would generate, and a computer would often do this, a line of best fit. So you might see a line that looks something like this, that sort of shows what the trend is, even though it doesn't necessarily connect our dots. So let's take a look at a graph that's a little bit improved from this original one. So this graph, although the axis is still wrong here, this really should be 0, 0 at this point. This graph is a little bit better. We've got a title. We can see that they've generated a line of best fit, so even though it doesn't really zigzag, but it kind of shows what the trend is. And now we have labels on our two axes, our x and our y. So that's kind of gives you a little preview about graphing data. So let's talk about graphing in our class. So there are many, many kinds of graphs, but there are two main ones that we would be using in here. The first one is a line graph. Now a line graph is specifically used when you're plotting what we would call continuous data. What you want to look for here is that in your experiment, your independent variable and your dependent variable, remember, your independent is the thing that you are changing. Sometimes it's called your manipulated variable. So your independent or manipulated variable and your dependent, which is, remember, sort of the data you are collecting, that variable, they're both numbers. So if they're both numbers, you'd want to make a line graph. So for example, you might have time in seconds and maybe the amount of product that's made. And this would also be some kind of a number. Maybe it's milligrams. This would be a line graph because we would be able to then see a trend that over a period of time, maybe the amount of product increases, something along those lines. So this would be a good example of where you'd want to use a line graph. So anytime you have a number for this, a number for this, you're typically going to use a line graph. On the other hand, let's say one of our two data pieces, or independent or a dependent variable, is not a number. So here you're going to want to use a bar graph. For example, let's say that you are graphing organisms that live in a forest, a bunch of species that live in a forest. Okay. So let's say we have our species here, and you sit in the forest and you're counting, and you count how many rabbits you see, and you count how many birds you see, and you count how many deer you see, and this is the number. Well, rabbits, birds, and deer are independent variable, the different species. That is not numerical data. So this would make more sense that you would make a bar graph, because really, it doesn't really make any sense to have a number of rabbits and a number of birds and then somehow you connect that. That doesn't mean anything, this distance in between here. So this is good for comparing separate discrete quantities. All right, now a little disclaimer. There are, again, many other kinds of graphs, a plot and whiskers graph, a scatter plot, a pie chart. But in here, the main two that you might be asked to draw would either be a line graph or a bar graph. All right, so more about graphing. Your independent variable, again, what you are changing in your experiment, that's going to be your x-axis. Remember, that's your horizontal line. Your dependent variable, your data, that's going to be your y-axis, your vertical lines. You cannot just put either variable on either axis. And we actually did this in class today, and some people had these flip-flopped. And when you do that, your data actually won't make a lot of sense. Your graph will not really be readable, so it's very important. You want to give it a title, something that kind of describes your data. And you also want to make sure that your labeling is proportional. In other words, if your numbers, let's just say your numbers here are, I don't know, 4, let's say 12, 13, and 22. Let's just say those are the data points you got. You wouldn't do this, 4, 12, 13, 22. That doesn't make any sense. Because if you make a distance here, and that represents 4, then this also, since it's the same distance, also has to represent 4. So you need to create a scale. If I know my biggest number is 22, come up with a scale so that I can get up to 22. Maybe you make a scale in 4s, 4, 8, 12, 16. Maybe you make a scale in 2s. Maybe, because you don't have enough space, you make a scale in 5s, 5, 10, 15, 20, 25. And then you can plot these data points. But that's very, very important because if you're making predictions about your data, for example, if I test, say, 10 minutes and 20 minutes and 30 minutes, and I get a line that looks like this, I didn't actually test 15 minutes. But I could predict what 15 minutes the data should be because I have a proportional y-axis. If I don't make this axis proportional, then I cannot make those predictions. My graph doesn't make any sense. So this is very important. So here are 2 examples. We did these in class. So let's say, example 1, you measure how many mosquito bites a person receives, person A versus person B. So maybe let's just say your experiment is that you heard that mosquitoes like to bite some people more than other people. So you get 2 people, you put them in a room full of mosquitoes, and you count how many mosquito bites they have after an hour. So what kind of graph will we make for this? Well, remember our rule. If our independent and dependent variable are both numbers, we want to make a line graph. If one of them's not a number, we're going to make a bar graph. So let's take a look. Well, we have number of mosquito bites, so that is a number, but our other variable is person A versus person B. That is not a number. So this would have to be a bar graph. Now, what axis should the number of mosquito bites go on? So remember, our other rule is that our independent variable, the thing that we are changing, that is our x. And our dependent variable, what we're measuring as our data, is going to be our y. So person A and person B, that's what we're manipulating. We are changing which person is going to put in the room. So this would be our independent variable. The number of mosquito bites, that is our data, so that is our dependent variable. So this number of mosquito bites, this should be our y-axis. So our graph would look something like this. Our independent variable would be the person, A, B, and then our number of bites would be our y-axis. One thing that might be helpful, think about it this way. Your x-axis, excuse me, you would already know the labels and the scale and everything for your x-axis before you even do the experiment. I already know I'm testing person A and person B. Technically, I cannot make a scale for my number of bites yet because I don't have the data. So if you think of it that way, that the one that you don't yet know the scale because you haven't collected the data yet, that is always your y-axis, your vertical one. So that might be helpful. All right, for the second one, you measure the height of plants after 1 week after they're placed different distances from a light. So we're actually going to take a light. So let's imagine, let me erase my work here so you can visualize this maybe a little better. Okay. So what I'm going to do is I'm going to have a light source. So imagine I have a light bulb here. And I'm going to take plants and I am going to place them different distances from this light source. So maybe I put one 1 meter away, 2 meters away, 3 meters away. And what I'm going to then measure is how tall they grow. So I'm looking at how basically the distance from light is affects the growth rate of our plants. So our type of graph, let's see, we're looking at height, that's a number, and it's after 1 week, and we're putting them different distances from a light source, that is also a number, right? Meters from the light source and height of the plant, both numbers, so this would be a line graph. Next, what axis should the height of the plant go on? So again, let's think about this. Our independent variable, the thing we're going to change, is our x. And then the data we collect, the dependent variable, is going to be our y. Well, the thing that we are changing, our independent variable, is going to be the distance from the light. That's our independent variable. So that's going to be our x-axis. And again, think about it. You could label this before you even do the experiment. You would say, okay, distance from light, and I'm going to be putting them at 1 meter, 2 meters, 3 meters. Now we can label our y-axis, our height. Maybe it's going to be in centimeters. But we actually cannot make a scale yet until after the experiment because we have no idea. Are they going to grow a little or are they going to grow a lot? We don't really know. So our y-axis, we wouldn't be able to make a scale until after the experiment. All right, so hopefully that gives you a little overview of which kind of graph, what variables should go where. Let me show you one more sample. So we did this example in class. Now I modified this a little bit because the numbers that were originally here didn't really fit on the plot that I gave you. So I redid this so that the numbers I'm giving you, you can make them fit properly on a graph. So if you want to pause it here and try this yourself, you can. But if you were in class and you're just reviewing, you can just go ahead and play forward. So this is our data. Now, our temperature, if this was an experiment, we would assume that what we were doing is we were putting fish at different temperatures. So this is our independent variable. We're going to place the fish at different temperatures. And then what we're going to do is we're going to count how many times their gills open and close. So what we're looking at is kind of the effect of temperature on their respiration, because that's how they breathe. They open and close their gills. All right? So here is an appropriate graph. It's a little bit messy because I had to try to do this on a board. But hopefully you can get the point here. So on our x-axis, first of all, it's a line graph. We have a number and a number. Our x-axis is our independent variable. That's what we were changing. We put the fish at different temperatures. Our y-axis is the number of openings and closings. Our title, gill movement at different temperatures. Okay, our label on our x, notice, don't forget, very important, don't forget your units. If they give you degrees Celsius, you also need to add that to your graph. Don't just put temperature, because technically there's Celsius, there's Fahrenheit, there's Kelvin. How do we know what temperature scale the scientist was using if we don't include the units? And then over here, the gill opening and closing per minute. Now, notice that the scales on the x and the y are not the same, which is okay. But I did create a scale. So I decided on my x-axis to go with a scale of 5s because I could see that my biggest number was 27 and I wanted to make sure I could get to 27. So by doing, actually it's in ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. I was able to get up to 27 so everything would fit on my graph. Sometimes you may have to make a box represent more than one. In this case, each box is a distance of 1 degree. Now look at our y-axis. My y-axis, I realized I had to go all the way up to 44. And I could see that if I did it in ones, it wouldn't get to 44. In other words, if I did 2, then 3, 4, 5, 6, 7, 8, 9, 10, I would not make it up to 44. So I decided to do my scale with every box representing 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I did not label each box, and that's okay. Just like here, I didn't label 1, 2, 3, 4, 5. That's okay. But I do have a scale, and notice my scale stays the same throughout my entire graph. So anyway, also notice, and I didn't mention this before, but this is also important, since my first data point is not until 10 degrees, notice how I left this blank here. It would actually be incorrect for you to do this. You don't actually know what the gill rate would be at the lower temperatures because you didn't test the lower temperatures. So you want to start your graph, your first data point and your line should only start here at your first data point. You want to leave this section blank. Now another thing you could do if you're like, oh, that looks so ugly, I don't want to leave it blank. You could do this thing where you make a break in the graph. In other words, this is 0. You put like a little break here, and then you start with 10. And then you go from there. then you wouldn't have a big gap.